So in our final video on this lecture of the Renaissance, the Reformation, and the Scientific Revolution, we want to get back to this question of the backdrop of the Renaissance and the Reformation as an important historical context in which the scientific revolution developed. We've been talking all along about the connections between the ancient world and the scientific revolution, whether that's the Greeks, the Egyptians, the Mesopotamians, the medieval world, with the spread of Christianity into Europe, with the spread of Islam, and by Muslim scholars and Arabic scholars preserving ancient information. And then we also talked about the importance of trade routes and connections from around the world. It's not until the Renaissance, the Reformation, the Age of Discovery that we start seeing long overseas sailing happening. All of these things are going to come together. So just to focus a bit on the Renaissance and the Reformation, the Ren and Ref, the Renaissance and Reformation, broke down that Christian unity in Europe. That could be a negative for science, that could be a positive. Whatever it is, it's a change. It's different from what used to be. Religious wars created challenges to both ecclesiastical, that's church, and political status quo. So the Renaissance, the Reformation, led to warfare or contributed to the development of political warfare as well. The scientific revolution represents a challenge to intellectual authority, perhaps ecclesiastical authority, and perhaps represents a new consideration of how states will patronize scientists, and that'll be something different from the ancient world. So a little background to the scientific revolution. Again, we have from the Renaissance this translation of ancient sources, particularly the Greek sources, into Latin and into other languages that people speak. Also, the background to the scientific revolution relates to magic and alchemy. The medieval world in Europe was something magical, as were some of the ancient societies we've looked at. And this idea of trying to harness the power of nature for the use of man, to the service of man, is related both in magic and in alchemy. Alchemy, the desire to change the properties of things found in nature. Renaissance artists attempted to imitate nature. Thus, they made a close observation of nature. So we've got people like Michelangelo, Leonardo da Vinci, doing close studies of anatomy, close studies of botany, plants, and how they grow, and geometry as well. Now we want to talk about some of the key players in the scientific revolution. So if our background is related to Europe as a whole in this time of the Renaissance and Reformation, there are some key players here. We've already mentioned Copernicus and how he's a Renaissance thinker, a Renaissance element. The other folks that we want to talk about are Tycho Brahe out of Northern Europe, out of the Netherlands. Kepler, also in Northern Europe. Galileo, Northern Italy. Newton, out of England. So all of these folks are key players. It is Newton who says at one point, I stand on the shoulders of giants, right? I could not have come to my conclusions about gravity, about the calculus, without all of these people ahead of me making their own contributions. So the scientific revolution is not just one person, not one place in space and time. It's a series of events, ideas shared throughout European society, shared because we have the printing press, shared because we're going to start to see individuals forming groups, societies at university, and also just for leisure, for fun, much like we would have today, book clubs, etc. We now have people gathering for social events where they're going to discuss science. Let's start with Tycho Brahe. It's a great image of him. So Tycho Brahe, he is, let me go up here first and we'll get back to his image. He is a fellow who's living in the Netherlands, and his approach to science was data collection. He set up an observatory. He was patronized by a local prince who gave him essentially a castle where he built an extraordinary observatory where he could take a look at Sorry, I said the Netherlands. He's in Denmark. Take a look at collecting data, watching the stars, keeping track of that. So this king of Denmark allowed him to build an observatory. He had students, he had assistants, and for 20 years we did data collections on the movements of heavenly bodies. The body of data led him to reject Aristotle and Ptolemy, as Copernicus had done. So it allowed him to reject that. And as he read Copernicus's material, he really could not accept all that Copernicus said. So let's take a look at what he did come up with. Based on his data collection, let me back up to this previous slide. Based on his data collection, what he came up with was the idea that the Earth was the center, and here's our Earth right here, and it was orbited by a moon, right? And then the sun orbited the Earth. Yeah, so we've got the sun in a perfect circle orbiting the Earth, the moon orbiting the moon orbiting the Earth. But then what we have over here is all the other planets circling the sun. So it's a very interesting attempt, if you will, to try to reconcile the two systems. One with a sun that is stationary, the other with an Earth that is stationary. And so he came up with this very interesting sort of like a Venn diagram approach. So that's Tycho Brahe. Again, what he's probably most famous for is this data collection and creating this observatory, again, with the help of state patronage in Denmark. A fellow who comes after him is Johannes Kepler, and Kepler has the great distinction of having access to all of Brahe's data. So again, building upon the past, building upon what other people have said. Brahe took Copernicus's idea and tried to come up with a different approach. Wasn't very successful based on the math. Kepler comes along and uses all that data that Brahe collects to come up with his own theories about planetary motion. Let's talk a little bit about Kepler. He was supposed to be a minister. Again, remembering that this is a very religious time, even though we have the chaos of the split between the Catholics and the Protestants. This is still a very religious time. He was destined to study to be a minister. In that process, he studied math and astronomy and was very much intrigued by math and astronomy. In particular, he thought that the harmony of the human soul could be mirrored in mathematical relationships between the planets. Let's say that again. Kepler believed that the harmony of the human soul was mirrored in the mathematical relationships between planets. Wow, right? So that's a little bit of that mystical, magical approach, if you will. It goes back to the music of the spheres, perhaps, that Pythagoras was trying to capture, if you'll remember that video on numbers and some of our discussion of the Greeks. So an interesting connection, if you will, between the ancient world and its philosophical attitudes and the world in which he was then living. So as we said before, he will have access to Brahe's data, and once he gets hold of that, he's going to make some observations based on that data, and what will result are his 3 laws of planetary motion. First off, elliptical motion. He says, if you look at Brahe's data, the heavenly bodies that we see seeming to move across the sky do so not in a perfect circle, as Aristotle had said, as Ptolemy had said, and even Copernicus. He says, no, it's not a perfect circle. Instead, it's elliptical motion. And what he noticed based on Brahe's data is that the speed of a planet increases as it gets closer to the sun, and it decreases as its distance from the sun increases. Now, he didn't know why, but by looking at the data, he understood that this is what happened, right? So the speed of a planet increases as it gets closer to the sun. The speed of a planet decreases as the distance from the sun increases. So the farther away a planet is from the sun, the slower it moves. And then finally, he said the square of a planet's period of revolution is proportional to the cube of its average distance from the sun. So the square of a planet's period of revolution is proportional to the cube of its average distance from the sun. So the revolution and the distance have a relationship, right? And it's mathematical. One of the interesting things about the scientific revolution is that we are going to start to see a transition in philosophy to thinking that philosophical proofs need mathematical support, right? This is a transition. This is a change in philosophy, that you need to be able to support your reasoning, if you possibly can, mathematically. This is going to be a very different approach to finding truth, to finding fact, than what had previously gone before in philosophy. Kepler, part of that. So this is Kepler's model of the universe. It's a little bright, sorry, but I like it. So what you have here, now he doesn't have all the planets in our solar system, but he accepts Copernicus's view that the sun is the center and the sun is stationary, and that everything else, including the Earth, and here we are right here, revolve around the sun, and do so in an elliptical fashion. Again, he's not quite sure why it's elliptical, but he just knows that it is, based upon the math and the data that Brahe has collected. So, Kepler's results, he destroys the idea that the planetary orbits were perfect and perfectly circular. He also destroys the idea that the motion of planets are steady and unchanging. Right? They do change. The closer they get to the sun, the speed changes. And the basic structure of Ptolemaic system disproved. So no longer can we accept the Ptolemaic system. No longer can we accept the Aristotelian system. Now we enter Galileo Galilei. And for Galileo and his contribution, we have to go to Italy. The image that you see here is of Padua, and perhaps one of the places where Galileo studied. We've been talking about science, and of course one of the issues associated with science is technology, and with Galileo, among other things, and your McClellan and Dorn will give you so much information on Galileo, you probably won't want any more. But among other things, Galileo is responsible for developing a telescope. Now, where did he get this telescope? Again, from the Netherlands. This time, originally this was a spyglass, right? A spyglass is something you use in navigation. It's something to look for distances. And he took a spyglass and turned it to the heavens. Now, he worked on it. He increased its ability to magnify, right? So he did work on some optics there. But when he turned his spyglass heavenward, he found the craters on the moon. Craters on the moon. Before this examination of the moon, people thought the moon was perfect. It was, in Europe in particular, and now we have some Muslim scholars who might differ, but in Europe people saw the moon as perfect, as all the heavenly bodies were perfect. And when Galileo turned his telescope that way, he found that there were craters on the moon. In fact, it kind of looked like there were elements similar to the Earth. He found 4 moons revolving around Jupiter. 4 moons revolving around Jupiter. So that was confirmation of how the Earth had its own moon. And it sort of was confirmation that while we have the Earth with its moon revolving around the Earth, and the Earth revolves around the sun, that Jupiter too has moons revolving around Jupiter, and Jupiter revolves around the sun. He found the phases of Venus. Venus we often call the North Star. Venus seems to be a fixed position in our heavens, but it actually has phases. And he noticed sunspots. Now, I'm not going to advise any of you to turn your telescope towards the sun, but the sun itself having interesting imperfections, if you will. So one of the things he did put forward is, well, what are planets made of? If they're not perfect and beautiful and smooth, what are they made of? And he came to the conclusion that they're made of similar things as is the Earth, right? So observation. This was one of the things that telescope allows, and Brahe's data allowed, was just observation of the heavens and recording that. This is a popular painting a little bit later than the Renaissance, but it shows the Doge of, golly, is this Florence? This a great leader of Florence, getting a first-hand tutorial from Galileo, and Galileo is here on the telescope, showing him how to use it. So again, reminding us of political patronage for scientists. Galileo is convinced that Copernicus was right and that Kepler was right, and so he publishes his findings in a book called The Starry Messenger, and he publishes his findings in Italian. So instead of publishing in Latin, which was sort of the language of science, he published in Italian, the language of his neighbors. He gained the patronage of the Duke of Florence, who was very, very wealthy and who was willing to support him in his research. And as he's publishing and presenting his findings, he draws attention from certain religious orders, in particular the Dominicans and the Jesuits. The Jesuits, you probably know, are very much interested in education. And not long after Galileo starts to publish and teach in a very popular fashion, Copernicanism is declared a heresy. Now, by the church. Now, you have to keep this in mind that we're living in a time of great volatility. We're living in a time of the Renaissance and the Reformation and political chaos, and the church does not like the idea of this new business of the earth being not only not stationary, but moving and revolving on an invisible axis, right? And rotating on an invisible axis and then revolving around the sun. This is just too much. This is too much chaos. It's one thing for the scientific community in universities, in these salons, in private conversation to have this, but when you start to publish this publicly and publish it in Italian, it could create more chaos, more confusion for the believers, right? So I find myself kind of apologizing for the church, and I don't really mean to do that, but this is just their reaction. An inquisition is formed to investigate Galileo and to investigate Copernicanism, and the findings are the following, and I've quoted it for you, that the doctrine that the sun was the center of the world and immovable was false and absurd, formally heretical and contrary to Scripture, whereas the doctrine that the earth was not the center of the world, but moved and has further a daily motion, was philosophically false and absurd, and theologically at least erroneous. So read that again. The doctrine that the sun was the center of the world and immovable was false, is absurd. Because the Bible, the scriptures talk about the sun moving. If you know your story of Joshua in the battle of Jericho, Joshua asked God to command the sun stand still so that he could finish the battle. Right? Luther in particular, Martin Luther found Copernicus to be outrageous because with the Bible as authority, how can you say the sun doesn't move? God says the sun moves. Right. So this is from the Inquisition, and for once the Protestants and the Catholics here are absolutely in accord. Another work of Galileo's, The Dialogue on the Two Chief World Systems, published in Italian in 1632, is the thing that really got him under house arrest, because in this one he presents in very clear, easy to understand terms the Copernican system and the Ptolemaic system. So he puts them out side by side and shows the flaws of the Ptolemaic system, the Aristotelian system that says the earth is the center of our world, right? So he blows out of the water mathematically, philosophically, that we are a geocentric system. This is when he's put under house arrest. As the video you have at Blackboard says, yes, indeed, oftentimes the punishment for heresy was death. But in Italy, with Galileo, he's just asked to stop publishing, he's asked to stop teaching, and to stay home. He kept working, he kept up his scholarly endeavors, but it was an unfortunate time in the history of the connection between the church and science. So Galileo on planetary motion, there's one other thing that we need to talk about. And he adds to those discussions that other scientists have made, basically Kepler and his elliptical motion. So Galileo is going to get us going on the concept of force. If a uniform force is applied to an object, it would move at an accelerated speed rather than at a constant speed. So an object that is in motion, if it has a force applied to it, it will move at an accelerated speed. So if you remember, Kepler said the closer an object gets to the sun, the faster it moves. Galileo says if an object is in motion, it will go faster if there is another force applied to it. We're not yet at gravity, but we're trying to get there. He also gives us the concept of inertia. A body in motion continues in motion unless it is deflected by another force. Took a little while for my last word to get down there. So inertia, a body in motion continues in motion unless it is deflected by another force. Right? So a uniform force applied to an object would move if a uniform force is applied to an object, the object would move at an accelerated speed rather than at a constant speed. And with regard to inertia, a body in motion continues in motion unless deflected by another source or force. That gets us to Newton, often called the last magician, the last of the medieval world. He's from England. He is around in the 17th into the 18th century. He's Cambridge educated. Oops, let me get back. He develops a new mathematical form. He develops the calculus. And the calculus is a form of mathematics, as you probably know, that helps us understand force, helps us understand change and the rate of change. So this is falling right in line with Galileo and Brahe's ideas. So it's going to be, again, taking yet one more fellow, one more observation, one more serious mathematician to try to figure out why the planets move the way they do. His main work is the Principia or Principia, and it was completed in 1686. And in this work, he applies calculus. He comes up with more laws of planetary motion and takes us full on to understanding the role of gravity. But just to give you a little more information about him, he was the warden of the Royal Mint in England, which meant that one of the things he was doing was looking for forgeries in metal coins, so gold and silver and copper coins. He was looking for forgeries, so trying to keep the economic system of England true and straight. Because he was working with metals and how to test metals, we think he also dabbled in alchemy a little bit. So considering him the last of the magicians, right, he's still trying to change the properties of things found in nature. He's the head of the Royal Society in 1703. The Royal Society is an actual, it's not a university per se, but it's a coming together of scientific scholars, mathematicians, natural philosophers who have patronage from the house. At this point, I think it's Hanover, the royal house, right? So the Royal Society, he's head of that in 1703, so he's quite important fellow, well known in many circles, and he was knighted in 1705 for his contribution to mathematics and physics. Yes, if you get to England, if you get to London, you'll find him buried in Westminster Abbey. So, a notable fellow in British history. His Principia or Principia is probably one of the most famous treatises on math in the history of science. John Maynard Keynes, you may know him as an economist. He did his thesis while at Cambridge on Newton, and he says Newton was not the first of the age of reason. He was the last of the magicians. He looked on the whole universe as a riddle, as a secret which could be read by applying pure thought. And again, he represents nicely for us a transition in philosophy in Europe, a transition from the older medieval ways of trying to figure things out, starting with the Bible as the ultimate truth, right? And now we're going to transition, not that we're going to leave God out of it, because Newton seems to be really very much a religious man, but we're going to incorporate mathematics as well to try to figure out how mathematics can help us understand the world around us. Keynes says, for Newton, God had laid clues about the whole world to allow a sort of philosopher's treasure hunt. These clues can be found in the evidence of the heavens and in its constituent elements, but also in certain papers and traditions handed down in an unknown chain all the way back to Babylonia. So Newton knew that many societies previous to him had been trying to work out these mathematical problems. And if one could just have the time and the wherewithal and the energy to study the mathematics of the ancients all the way up to the modern time, one could figure things out. Mathematical Principles of Natural Philosophy, that was his big book, the Principia for short. He offers proofs demonstrating the universal law of gravitation. Right, and that's the big key for all of this. That's that force that Galileo's talking about. That's the reason why Kepler was able to detect the elliptical movement. His work is the culmination of the theories of Copernicus, Kepler, and Galileo. He has 3 laws of motion, and we'll go through each one of them. Every object continues in a state of rest or uniform motion in a straight line unless deflected by a force. So all objects continue either in a state of rest or in a state of uniform motion unless deflected by a force. Right? So I think we understand that. The rate of change of motion of an object, is proportional to the force acting upon it. So, makes sense, right? So if you're driving a car and you push the gas pedal a little bit, you will go slowly. If you're driving a car and you floor it, you will go quickly, right? So the rate of change of motion of an object is proportional to the force acting upon it. To every action, there is always an equal and opposite reaction. And again, these 3 laws of motion come to Galileo through observation of data, through philosophical application of math to the data he's found. So let's take a look at this video for a moment.
Sir Isaac Newton was a scientist who lived from 1642 to 1727. He developed the 3 basic laws of motion and published them in 1687. Newton's discoveries helped to start a scientific revolution and led to the fundamental understanding of how bodies move through physical space. The first law of motion, the law of inertia. Objects will remain at rest or in a uniform motion in a straight line unless acted upon by an unbalanced force. Here we have 3 spheres on a table in a state of rest. The gravity pulling the spheres down is countered by the force of the tabletop pushing the spheres up in the exact opposite direction. The balance of forces is what keeps the spheres at rest on the table. This sphere will act as an unbalanced external force. Without another force to counter its movement in the opposite direction, it becomes an unbalanced force acting on the other spheres. The external force collides with the spheres and changes their motion state. The natural tendency of an object to remain at rest or in a uniform motion in a straight line is called inertia. The second law of motion, the law of force, mass, and acceleration. The acceleration of an object depends upon its mass and the magnitude of the force applied to it. When an unbalanced force acts upon an object, the motion of the object changes. The rate of this change over time is called acceleration. Acceleration depends upon 2 variables, the mass of the object and the magnitude of the applied force. In this example, a 3D character represents a pulling force on a 50 kilogram mass. Using his full strength, he has no trouble accelerating the object in the direction of his pulling force. If the mass is doubled and we want to accelerate it at the same rate, we must also double the force. Our character, however, is already pulling at his full strength, So what happens? He can only accelerate the object at half the rate as illustrated by his slower pace. This relationship between force, mass, and acceleration is the source of one of the most important equations in physics. Force equals mass times acceleration. The third law of motion, the law of action and reaction. For every action, there is an equal and opposite reaction. A direct example of the third law is the rocket engine. Look at the hot gases streaming out of the shuttle's engines. If this is the action, what is the equal and opposite reaction? It becomes clear as the shuttle is propelled into the sky. The reaction to the gases escaping from the engine is the pushing of the spacecraft in the opposite direction. Everywhere you look, these laws are being followed by everything around you. With some extra awareness, you may begin to recognize your own use of these laws in your daily life.